Hello everyone. In the last lecture we discussed the properties of real gases. In today's lecture we'll start the laws of thermodynamics. Now before we discuss what is thermodynamics, what we study in thermodynamics, we'll first define few terminology that we'll be frequently using. Now we'll first discuss definition of thermodynamic terms. And as we told in the very beginning, that thermodynamics tells us about the interaction of a macroscopic system with its surrounding. Now, what do we mean by a system and surrounding? Now, a system is defined as part of that physical universe, the properties of which we are investigating. What does it mean? Suppose we are discussing the expansion of a gas and the gas is put in a container. Now that gas is the system here, and then what will be the surrounding? The surrounding will be the immediate environment that the gas has. Actually, it is not only the immediate environment, it is the rest of the universe, because it is said that the system is confined to a definite place in space by a boundary which separates it from the universe, which is called as surroundings. But usually the effects will be observed in its immediate environment, which is just outside the boundary. Now this presence of the boundary is very crucial, because the boundary is the thing that defines the separation between the system and the surrounding. Now, depending on the nature of the boundary, we can have different types of systems. For example, open system, closed system, and isolated system. A system is called an isolated system if it produces no observable effect or disturbance in its surrounding. Now, what will be a perfect example of an isolated system? There is no such perfect example, but we can think that suppose there is a gas in a container which is thermally insulated. So there will be no heat exchange with the surrounding, and of course since it is in a container, there will be no mass exchange also with the surrounding. So we can say that that system is an example of an isolated system. Now think about it, the universe as a whole is an isolated system because there is no surrounding of the universe. By surrounding we mean the part of the universe which is not a part of the system. So the rest of the universe is surrounding. So universe as a whole is also an isolated system. Now what is a closed system? A closed system is when the system does not exchange any mass with the surrounding. We just gave you an example of the system at the very beginning, that consider a gas in a container. So this gas, if we confine it in a container, no gas molecule will come outside, and also no new gas molecules from the environment will enter that container. So that system of gas molecules inside the container can be thought of as a closed system. Now remember that for a closed system, the system can exchange heat with the surrounding, which means the wall has to be now thermally conducting. If the wall is insulated, then the system is an isolated system. Now what about open system? A system is called an open system when mass passes across the boundary. Now think about a living body, like our body. We breathe, we take oxygen, we inhale oxygen, and we breathe out carbon dioxide, which means we are constantly exchanging mass with the surrounding. So any living system is an example of open system. Now let us define some other terms. What is very important in thermodynamics, as we discussed, is the interaction of macroscopic system with its surrounding, and during this interaction there is flow of heat into the system or into the surrounding. Now heat is defined as follows. We explain the attainment of a thermal equilibrium of two systems by asserting that the quantity of heat, which we denote usually as capital Q, from the system of higher temperature to the system of lower temperature. So there is no such definition that how much heat a system has. Heat has only meaning when a transformation happens. We'll discuss it in detail immediately. Now, here are some properties of heat. Heat appears only at the boundary of the system. What does that mean? That means in any process or any process that involves a change of the state of the system, heat will either flow into the system from the surrounding or to the surrounding from the system. So the heat flows across the boundary, and that is what we are going to quantify. Secondly, heat appears only during the change in state. That's what we already discussed, and that means when a system is in thermal equilibrium, we cannot say that how much heat it has. That's a meaningless question. Only when the system does a transition, then only we can ask a question how much heat is absorbed or how much heat is released. Thirdly, heat is manifested by an effect in surrounding. So remember that there is a system and there is a surrounding, and we are going to do some experiments on the system. Now we have to see the effects of these changes which we are performing on the system. However, these changes are observed in the surrounding. Due to the change in the system, there will be an effect in the surrounding. For example, if we do a process in which the heat is absorbed by the system, then the temperature of the surrounding should go down, and that is the meaning what we say here, that heat is manifested by an effect in the surrounding. Number 4 is the quantity of heat is proportional to the mass of water in the surroundings that is increased by 1 degree in temperature, starting at a specific temperature under a specified pressure. Now this thing you have studied, how much heat you need to raise the temperature of water. Why water? Because the specific of water is maximum, and for a finite change in temperature we need a sufficient amount of energy, which is heat in this case, to raise the temperature for water. So that's just an operational concept how we'll measure heat. Number 5, which is most important, is that heat is an algebraic quantity. Means if in a process or in a series of process we first see that heat is released by the system and eventually heat is absorbed by the system, we can take the difference and ask the question how much net heat it is absorbed or released into the system, which means we can add or subtract the amount of heat released or absorbed. So that means mathematically heat is an algebraic quantity. Now we'll follow a convention here. It is positive if the mass of water in the surrounding is cooled, which means surrounding getting cooled means the temperature of the surrounding is falling down, which means heat has flown from the surrounding into the system, and that we take as a positive quantity, which means in which case we say that the heat has flowed from the surroundings. And the opposite thing is if the heat is flown from the system into the surrounding, so the mass of the water will be warmed up, so the temperature of the water will rise, in which case we say that the heat flow or the associated change in heat has a negative sign. So this is a convention again which we will be following throughout this course. Now just like heat, we also can define another quantity of energy, which is work. Usually in thermodynamics, we'll constantly be discussing how heat is converted into work or work is converted into heat, because that is the main purpose if we want to create or develop a heat engine. Now let us define what do we mean by work. In this case, we'll make an analogy with mechanical work. We are going to describe each term in very detail with examples very soon. Now in thermodynamics, work is defined as any quantity. By quantity I mean here any energy quantity that flows across the boundary of a system during a change in its state and is completely convertible into the lifting of a weight into the surrounding. Now we'll give you an example where the lifting of the weight will be connected to the expansion or compression of a gas and the associated heat flow. Now lifting of a weight means actually it is a mechanical work. So we'll draw an analogy between the mechanical work and thermodynamics. As before, we pointed out some properties of heat. Here we are pointing out some properties of work that we have to keep in mind. Now remember, work is also a form of energy just like heat. So work also appears only at the boundary of the system. And the logic is just like we provided for heat. Similarly, work appears only during a change in state. There is no meaning if I ask a question how much work a system has. The system performs work only when it transforms a change in state. Similarly, just like heat, work is also manifested by an effect in the surrounding. In this case, we will show that the masses in the surrounding are lifted up or down if work is performed or work is destroyed. The quantity of work is equal to W is equal to minus mgh, where m is the mass lifted, g is the acceleration due to gravity, and h is the height through which the weight or the mass has been raised. Now notice this minus sign, which is very important here. In many older textbooks, you will see a definition of the work is W is mgh. So we'll not use this definition in this course. We'll use the more modern definition where the work is defined as negative of mgh. We'll discuss why we are taking this negative sign in detail. Just like heat, work is also an algebraic quantity. You can ask this question if for a series of processes, work is performed by the system and then in the next process work is done on the system, how much net work has been spent on the system or how much net work the system has performed. So mathematically saying work is an algebraic quantity. We'll consider it as negative if the mass is lifted. This is very important, which means the height is in this case should be negative because the height we are lifting, but we'll take it as a negative quantity. We'll come back to it. In which case the work has been produced in the surrounding or has flown into the surrounding. We'll take it positive if the surrounding performs an work on the system, which means masses will be lowered in the surrounding. Now remember that again, this is a convention. Just like for heat, we took a convention earlier. For the convention of the heat, remember that when heat is flown into the system, we took it as a positive quantity. So keeping an analogy with that, in the newer convention, we are saying when the work is done by the surrounding on the system, we'll take it as a positive quantity. And in order to do that, we have introduced this minus sign here, which will be clear in a moment. Now, let us first discuss the zeroth law of thermodynamics. Now, this sounds a little bit odd. What is a zeroth law? The reason being, when thermodynamics was developed in the mostly in the 18th century and 19th century, people first realized the law of conservation of energy and subsequently the directionality of a process, which they termed as first law of thermodynamics and second law of thermodynamics, which we'll eventually cover. Now, later on, scientists realized that a more fundamental law exists, that is the law of thermal equilibrium. And since already they have termed the law of conservation of energy as the first law of thermodynamics, they called the more fundamental law, as which is basically the law of thermal equilibrium, as the zeroth law. Now let us try to understand very conceptually what is the zeroth law. Let us consider a system. Now in this case we will be frequently using this system, which is a gaseous system in a container. Now suppose we have a container and in this container there is a gas and the volume of the gas is V1, and attached with this container is a pressure gauge which denotes the pressure. Suppose initially the pressure is P1, and now what we do is we bring in another system of say volume V2, which as before is connected to a pressure gauge, and suppose the pressure reading for that is P2. Now what happens if we now imagine initially these two systems, which we call as system A and say system B, are far away from each other, so they are not in contact. Now suppose let us bring them in contact, and what happens? Since the container volume is fixed, the volume of the gases will also be fixed. They will not change. And now consider a wall between them, that is thermally conducting wall. So if it is thermally conducting, heat will flow or heat can flow across this boundary because it is thermally conducting, and as a result the pressure will show some change in the reading in these two systems, which we call as P1 prime and P2 prime. So P1 prime and P2 prime are the final pressure of these two systems. Now consider that we begin with a three system, where the first system, as before, we denote as A, and then the second system as B, and the third system as C. Now in the earlier case, when we touch these two systems or make a contact through this of these two systems through this conducting wall, and as I said that heat can flow freely across the boundary, which means now the system A and B are in thermal equilibrium, and since they are now in thermal equilibrium, in order to maintain the thermal equilibrium, the pressure has changed for system 1 or system A from P1 to P1 prime, and for system B from P2 to P2 prime. Now suppose a similar condition where system A and B are connected through a conducting wall. Similarly, system B and C are also connected through a conducting wall, and we are also measuring the pressure for these systems, which are showing some readings, say PA, PB and PC. Now what is the situation here? A and B are in thermal equilibrium, which means heat can flow across the boundary, it must flow. That's why we chose a conducting boundary. Since B and C are also in thermal equilibrium, heat should flow also across this second boundary. The Zeroth law says if two systems, say A and C, are in thermal equilibrium with another system B, the two systems should also be in thermal equilibrium with each other. What does it mean conceptually is that this is equivalent to drawing that this system A and this system C are also in thermal equilibrium, although they are not directly connected through an thermally conducting wall. So here we get the actual, so let us see the actual statement of the Zeroth law of thermodynamics. So the Zeroth law says two systems that are both in thermal equilibrium, these two systems we chose, remember, as A and C, the two systems which are both in thermal equilibrium with a third system which we chose as B are in thermal equilibrium with each other, which means A and C are also in thermal equilibrium. Now you have already learned the ideal gas equation. So if you think that this gas behaves ideally, initially what we did in the initial example was that I had two systems A and B, remember, as drawn here, and then I had a pressure P1 for the first system and P2 for the second system. And you know that since the volumes are not changing, in the final state I had P1 prime and the same volume for the system A, and for system B I had P2 prime and the same volume since the volume did not change. Now since PV equal to RT and since R is a constant, what we meant by that is P1 V1 initially cannot be equal to P2 V2, because if they are equal, the temperature of the system A and system B must have been equal. Then the systems are already in thermal equilibrium and there should not be any change in the pressure. So initially our choice was P1 V1 was not equal to P2 V2, and that's why when we brought them into thermal contact, we found a situation that the pressure of each of the system changed, which means under thermal equilibrium, since they have the same temperature, which is suppose T, so P1 prime V1 is equal to RT, also P2 prime V2 is equal to RT. So we have arrived at a condition which is this. So in order to do that, the pressure of system A and the pressure of system B has changed from P1 to P1 prime and from P2 to P2 prime. So this shows just conceptually that if the systems are in thermal equilibrium, the temperature must be the same for those systems. So we have some operational definition for temperature. The system in thermal equilibrium with each other have the same temperature, and systems which are not in thermal equilibrium have different temperature. In this example which we had shown, initially the systems had different temperatures. That's why P1 V1 was not equal to P2 V2, and moment we brought them in thermal contact through a conducting wall, heat flew across the boundary, and then the flow of heat brought the temperature of the two systems equal, and now the systems are in thermal equilibrium. So this is a conceptual explanation based on a thought experiment that we just did. So again, the Zeroth law says that if the two systems are both in thermal equilibrium with a third system, then the two systems must be in thermal equilibrium with each other. Now let us move on and start the concept of work. So far what we have discussed is the concept of heat flow and the associated temperature. So the heat flow has a meaning only when there is a concept of difference in temperature. If the temperatures were equal for two systems, there won't be any heat flow. Now let us consider how we will quantify work. In this case, as I said, we will be talking about the pressure volume work. Now again, remember that the convention is if the work is done by the system then we'll call it as a negative work, and if work is done on the system by the surroundings, then we'll call it as a positive work. And for that we asserted that the definition of the work, in the definition of the work, we have to insert a negative sign. Now think about again a system or a hypothetical system which is a gas in a container. In this case, think about the container as a cylinder. So this is a gas inside this container which has a certain volume, and this is the cross-sectional area of the base of the cylinder, which we call as, say, A for area. And what we have done is that we have put a mass on a piston which is lying at the top of the cylinder. And of course this mass is not falling because we have put, say, some pin here which we can remove. So this will be our hypothetical system, which is a gas confined in a cylinder. Now frequently we'll be drawing it as a simple drawing where we will not show the area. So this is the piston, and a mass is kept on the piston, and there are two pins which hold this piston, and the gas has certain volume. So this is our system. So rest of the universe which is outside this system is called surrounding. Now this piston will also assume has no mass, meaning all the effect of the mass is coming from this mass. So this is a very idealized situation. And secondly, when the piston moves up or down, if we remove those pins for example, and if the mass is creating a higher pressure than the gas, then of course the piston will move down. We'll discuss all those things. And during the movement, we'll also assume that there is no friction of the piston with the wall of this container. So the piston is actually massless and the motion of the piston is frictionless. So there is no dissipation of energy due to the movement of the piston alone. And also there is no force or created on the gas due to the weight of the piston because the piston is massless. Now let us try to consider how will you quantify work. Now think about it. Suppose this is our system and this is the piston, and then we have kept a mass on it, and suppose the pins are connected like this. In this case, the pressure inside this pressure of this gas, which we denote as say Pi, I is for initial pressure and the associated volume as Vi, the pressure is enough to raise this mass, which we denoted as M. We have been using the mass as small m, so let us just write it as small m instead of capital M. Now suppose we let these pins away and assume that there was another pin which was lying here. So what will happen? The gas, since the pressure was higher enough to hold this mass, so the gas will now expand, okay, because the mass alone cannot hold this piston, and which means the gas will now expand and come to a situation where the piston will now touch these pins. So the mass is now here. So as you see, the mass has been now lifted in the surrounding, which means the gas has done some work. We have to show that this is a negative work, and we have to also quantify what do you mean by the work. Now let us look at the change in the height of the piston. As you can see that the gas has expanded and the piston has moved by an height which we call as h. So in this case, the work done in our convention will be minus mg into h. Now you can divide it by the area of the cylinder and again multiply by the area of the cylinder. Now remember, if I do that, what is this quantity? What is mg? Mg is nothing but mass times acceleration. So mg represents the force acting on the gas through the piston. So force by area is nothing but the pressure. So mg by A is the pressure. In this case, this is nothing but the opposing pressure or external pressure. So instead of writing it as P, we'll write it as P opposing, or sometimes we'll write it as PEXT, which means it's an external pressure. This is not the pressure of the system or pressure of the gas. This is the pressure created by this mass on the system. Now what we have in the second term is A times H. What is A? Remember that A is basically this cross-sectional area of the piston. And what is H? H is change in height. So area times length is nothing but volume. In this case, it is the change in height. So area times height, or H, change in height, is nothing but the change in volume. So what we got is an expression for the work done as minus P opposing or minus P external into delta phi, where P opposing or P external is the external pressure that was acting on the system during the expansion or compression. We'll also talk about compression, means during the change, the acting pressure that is denoted as P opposing or P external, and delta phi is the associated volume change. Now suppose the final volume we denote as Vf and the final pressure as Pf. In this case, of course, Vf is greater than Vi because the gas has expanded. So delta V is nothing but Vf minus Vi, which is greater than 0, which means the work done here is negative. This is in accord with our convention that if the work is done by the system, we'll take it as negative. That's why we had to introduce this negative sign. Now this is clear why we took the negative sign in the expression for work. Now we'll discuss what will be the amount of work for the case of compression? Again, it's a pressure volume work, remember that. So let us try to draw it. So in the case of compression, we have an opposite situation. So initially, suppose the volume was Vi according to our convention, and then the piston was held by two pins and there was a mass. Now of course this mass is creating more pressure. That's why if we remove the pins, the mass will fall. And let us put two more pins so that the piston will fall up to a certain height. So if we suddenly remove these two pins, what will happen is that the mass will fall up to here, shrinking the gas, so the volume of the gas will reduced. And as before, let us just calculate. I was using small m notation for the mass. So as before, the work done will be minus P external into delta V. Now in this case, what is delta V? Delta V is change in volume, which is V final minus V initial. But note that here V final is less than V initial, which means that this work must be positive, because this is a negative quantity and we have a negative sign. External pressure cannot be negative, it is always a positive quantity. So now the work is done on the system by the surrounding, and this is consistent with our definition that we'll take this work as a positive work. So that's the importance of this negative sign.